Hey everybody, it's Dan from SageMathTutoring.com, and this is a video that I'm doing for a student of mine, a Skype student of mine, who is taking a test soon, and these are some of the problems that might be featured on the test, and these are problems that she has sent to me. So some of the pictures are a little bit blurry, but we are going to make do with what we have, and whenever I have time, which is not often, I will make a YouTube video covering some of the concepts. So anyway, hopefully this could be helpful for some of y'all out there. So let's begin. So looking at this first problem here, probability and statistics, what is obtained by multiplying the standard deviation by itself? So at a certain point in your mathematical career, it becomes important to realize that the standard deviation squared is equal to what's called the variance. For this test, it's not really necessary to really understand the details of what this means. What is more important is that you understand this relationship, which is one of the first things you need to understand when you're learning statistics. So, and this actually it happens to be the answer to the question. Something that the teacher will typically make you memorize happens to be the answer to this question. So what is obtained by multiplying the standard deviation by itself? Well, multiplying the standard deviation by itself is the same as squaring the standard deviation. So clearly the answer is the variance right here. Moving on. The bar charts below represent which data set? So let's take a look at this thing. So we've got people of 41 years of age. There's one of these people in the data set. 42 years of age. There's two people of 42 years of age. So this is a frequency chart here. So let's see. Basically, the way to read this, and this is directed especially towards my student, is you have a group of people. Some of them are 41, 42, 43, 44, and 45 years old. This frequency y-axis right here tells us how many 41-year-olds there are in your set, how many 42-year-olds there are in your set, and so on, 43, 44. So clearly there's one 41-year-old, there's two 42-year-olds, there's three 43-year-olds, and there's two 44-year-olds, and so on. So you just have to look at the answer choice that fits that situation. I would immediately, use process of elimination since the test is timed, so this is gone, obviously. This clearly doesn't have enough people. And then I would scan for the answer choices that feature one single 41-year-old. Now you have one there and you have one there, but this one already has like the number 1 as though there's somebody who is 1 year old. So answer choice 3 is out. And that leaves us, of course, with answer choice 4. So you could sort of use process of elimination as well, because there's no 1-year-olds here, there's no 2-year-olds here, there's no 3-year-olds here. So this next one's kind of interesting. How many 3-digit odd numbers are there? Assume that the digit on the left cannot be 0. So 3-digit odd numbers, it's important to recognize that the first 3-digit odd number would be 101, and the last 3-digit odd number would be 999. So I think that's important to keep in mind. What I would do to kind of get clear on this, it could be that there's some formula that is escaping my mind right now that would allow you to quickly figure this out, but let's see if we can extract a formula by experimenting with a simpler case. And a simpler case would be to find out how many 1-digit odd numbers there are. So the first 1-digit odd number is 1. The next 1-digit odd number is 9. And we could always ask ourselves, all right, well, how many 1-digit odd numbers are there? Well, the reason we're investigating this simpler case is because we could easily actually list them, right? 1, 3, 5, 7, and 9. And what I'm going to do is also list the even numbers just to get a sense of, the reality of what's going on between these parameters. And then we've got 10, right? And let's not forget that we have also a 0 over here, right? So one thing you could sort of do is get clear on what I would call the outside parameters here. And the outside parameters are this number right here and this number, because we're kind of taking interest in this area right here, because we're interested in the one-digit odd numbers. This is the list of all the one-digit numbers. And how many one-digit odd numbers are there? There's 1, 2, 3, 4, 5. So one way of doing that, one way of arriving at the amount of one-digit odd numbers there are, is you could take this outside parameter and you could subtract this outside parameter and then divide the result by 2. So in other words, you could take 10 minus 0 and then divide that by 2. So this is a decent formula. You could take the large, we'll call it OP for outside parameter, minus the smaller OP, and then divide that by 2. So that should work if you're trying to find the amount of blank digit odd or even numbers. So in this case, the larger outside parameter would be 1000, and the smaller outside parameter would be 100. So we could take 1000 minus 100 and divide that by 2. Now that would end up becoming, what is it, 900 divided by 2, which is equal to 450. So for my student, I would recommend using this formula right there. The larger outside parameter, in the smaller case, or in the simpler case, it was 10. Subtracting the smaller outside parameter, in the simpler case, it was 0. Because once again, we were studying one-digit numbers, right? And then dividing that result by 2. That should work. So, of course, the answer in this case is 450. Moving on. Question 4, probability and statistics. What is the mean of the following data set? So when they say mean, what that means is the what is typically referred to as the average. Okay, so back in the day, you may have learned the average of numbers. The mean is a little bit more complicated of a concept, but just know that it means we could call it the old school average, where it is the sum of values divided by the amount of values, right? This is something that should be relatively easy. It might be a bit tedious, though. So you're going to have to add all this stuff up. It's going to be 46 plus 53 plus 61 plus 100 plus 61 plus 53 plus 46. And then you're going to have to divide it by 1, 2, 3, 4, 5, 6, 7. So let's see. I'll write that out. I'm not going to bother with the calculation, actually, because I think my student sort of understands this. But let's at least write the setup, because I think that that's really helpful. Plus 61 plus 53 plus 46, and then you're going to add all that up, and whatever you get, you're going to end up dividing that by 7, and that's going to pump out your answer. All right, so moving on. Probability statistics. 9 runners are competing a race. Which formula is used to, let's see, the writing. Compute the number of ways in which the first place, second place, and third place trophies can be awarded if there are no ties. All right, so first place, second place, and third place trophies, also known as, gold medal, silver medal, bronze medal scenarios, that is a classic permutation scenario where the order does indeed matter. When the order matters, it's a permutation. When the order does not matter, it is a combination. All right, this is something that my student and I had sort of gone over before. Now, why does the order matter in this case? Sometimes it's helpful, especially if you have like a first place, second place, third place scenario. I like to write these sort of like underlines that represent the event of winning first place. So this is the event of winning first place. And this is an underline that represents the event of winning second place. And this is the underline that represents the event of winning third place. Now let's say that the names of the athletes, how many? There's 9 of them. Literally their names are, strangely, A, B, C, D, E, F, A, B, C, D, E, F, G, H, I. Okay, so the reason order matters, because let's say that this is, these are 3 underlines that represent the event of winning first, second, and third place. And you could even literally think of like these being the, how in the Olympics the first place winner is like standing a little taller, and then the second place winner is, happy but not as happy as the other person, and the third place winner is just this poor bastard that's like right here. So first place winner, yay. Second place winner, third place winner. So these underlines are akin to this sort of hierarchical thing that you would actually see once the race is over. And the reason why the order matters is because let's say that the winners end up being this person, and this person, right? Let's say, now, I mean, and under other circumstances, it could have been B, C, and F, but let's say it so happens that the winners are A, E, and G. Well, you could list them, right? You could be like, okay, well, A, E, and G, right? These are the winners. Now, using the same winners, imagine we listed it in a different order, right? Well, it's the same winners, but it is not the same situation. Because even though it's the same group of 3 winners, when you change the order that they're listed in this scenario, in this hierarchical structure scenario, everything changes, right? A getting first, E getting second, and G getting third is not the same situation as E getting first, G getting second, and A getting third, even though we're dealing with the same 3 people. That is why, in this case, the order matters. And when the order matters, you are dealing with a permutation, not a combination. So the question is, okay, great. What do I do when the order matters? Where there is a way of kind of figuring out, how many permutations there are, okay, which we could discuss later if need be. But notice how the question doesn't really require us to make that calculation, because let's see, what is it asking? It's only asking which formula is used to compute the number of ways in which the first place blah, 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 right? So the question's only asking which formula is used, right? So on this test, you have to be careful to not do too much work. You don't necessarily need to do the calculation. All you need to do is figure out which formula you're using. Now, the reason I had stressed whether or not the order matters is because we want to know, is it a permutation or a combination? Because obviously, if it's a permutation, we're dealing with P. If it's a combination, we'd be dealing with C. So we could immediately eliminate answer choice 1 and answer choice 2. But then the question remains, all right, well, is it, 9P, it's hard to read, but I think that's a 3, or is it 9P9, right? Well, this could be a matter of just simply memorizing the mathematical nerd language and recognizing that, the answer would indeed be this one, where it's like 9P3, because you can think of you're choosing 3 winner slots from a total of 9 runners, right? Well, let's say we're picking 3 winners from a total of 9 athletes, right? So this number on the bottom right represents how many people or elements you're picking from the set, and this number represents how many are people or elements are in the set, okay? That's the way to think about it. This is 9P9, which is absolutely irrelevant to our situation. Hopefully that helps. Okay, so consider the following weights in pounds of certain numbers of a football team, 180, 190, blah, 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 blah. The 60th percentile is given by which weight? All right, so if you want to find a blankth percentile, the first thing is you got to put the weights in order. Now, it looks like they're actually being very nice to us because it's already in order for us, which is great, all right, because it's a pain in the butt putting them in order. So here they are in order, which is great. Moving on, how do you find the 60th percentile? Well, actually, you have to count how many weights you're dealing with. That's the first step. And then you're going to have to find 60% of whatever that number is. Now, there are 10 weights, and we need to find 60% of 10. And that would be 0.6. I think a lot of y'all could do this in your head. A lot of y'all know it's 6, but just for the sake of thoroughness, we're going to actually do the calculation. That's going to be 0.6 times, because the word of typically means times, and then 10. That would end up giving you 6. All right? So here's the deal, though. When it comes to percentiles, when you end up with a whole number here, it's going to be different than what you have to do if you end up with a sort of decimal number here. For the sake of efficiency, I'm going to just cover what you would do in this situation if you end up with a whole number here. Privately with my client, with my student, I'm going to discuss with her what you would do if you didn't have a whole number here. But since we're trying to be quick with this video, we're only going to focus on the problem at hand. So anyway, you've got this whole number here. When you have a whole number, you have to count that amount of spaces over. So it's like 1, 2, 3, 4, 5, 6. But since it's a whole number, you have to do this sort of extra step where you're going to take the average between the number you just landed on and the next one. All right? We're going to take the average of the number we just landed on due to this whole number 6, which ended up being 235. And we're going to take the average of that with the next one. Now, some of y'all might be able to do this in your head. It's clearly 240. But just in case we're not clear about that, it's going to be 235 plus 245. And then it's going to be that divided by 2, because that's the average. You take the two numbers, you add them, and then you divide it by however many numbers you're adding, which happens to be 2. And if you were to go through the motions, it would indeed churn out a 240. So that's that one. Once again, with my client, I'll go over what we need to do if this number ends up being a decimal, which is a little bit different. All right, so question 7, probability and statistics. A person is dealt 2 cards from a regular 52 card deck. What's the probability of getting 2 clubs? Right. Well, there's 2 events happening. That's the first thing that comes to my mind. There is the drawing of the first card where you take a card out, and then there is the drawing of the second card where you take the second card out. And usually the way that, often with probability problems, it's going to be a matter of finding the probability of the first event and then multiplying it times the probability of the second event. That should work in this situation. So let's find the probability of the first event. So the first event, first of all, probability just in general, let's make sure we're clear about this. It's always the desired outcome, it's one way of wording it, over the total amount of possible outcomes, right? I find when doing probability problems, it's often easier to kind of figure out what the possible outcomes are first, because it's kind of a little bit more obvious. So we know that the possible outcomes for this fraction right here is going to be 52, because there's 52 cards in the deck. And also I can immediately see that the possible outcomes for the drawing of the second card is going to be 51. So as soon as these things come to my mind, I just write it down just to sort of stay in the flow. Because think about it, after drawing the first card, how many possible cards do we have to draw from later? It's going to be 51, right? And we know that possible outcomes goes in the denominator. So then we need to analyze, the desired outcomes. Well, that has to do with how many freaking clubs are there in a deck, right? I believe that would be 13, yeah, because a club is a suit, and there are 13 cards per suit, right? There's 13 hearts, there's 13, um, spades and all that. So this would be 13 out of 52 for the drawing of the first club, right? But then on the second drawing of a card, you will have 51 cards to choose from. And by the way, you're not going to have 13 clubs anymore. At that point, you only have 12 clubs left in the deck. So these are the fractions that you're going to have to multiply in order to find the answer. So anyway, I'm not going to do it for the sake of moving on, but if you were to use a calculator, maybe turn this into a decimal, maybe turn this into a decimal, and then multiply them together, and you're going to get one of these answers right here. All right, this is atrociously blurry, but we will work with it. So a restaurant offers a selection of 8 side dishes. Entrees come with the customer's choice of 2 side dishes. You must compute how many possible sets of 2 side dishes can be ordered. Will you use a combination or permutation? So the question here, despite the blurriness, is relatively simple once you understand combinations and permutations. So let's get clear once again on what the heck is going on. So a restaurant offers a selection of 8 side dishes. So let's say that the 8 side dishes, we're going to stick with letters, are literally A, B, C, D, E, F, G, H. And you get a choice. Looks like entrees come with the customer's choice of 2 side dishes. You must compute how many possible sets of 2 side dishes can be ordered. Are you going to use a combination or permutation? So what they're saying is, here are the 8 total side dishes that could be chosen from, and you're going to end up choosing 2 of them, right? And we want to know, in order to find out how many different pairs of side dishes we will choose, are you going to use permutation or combination? Now, as you may recall, I had already mentioned that permutation is when the order does matter. Like, for example, first place, second place, third place winners in the Olympics. And combination is when the order does not matter. Now, I can tell already this is going to be a combination problem, and I'm going to explain why. Because let's say that this is the event of choosing one side dish, and this is the event of choosing the second side dish. And let's say the 2 side dishes that you end up choosing are F and G, right? F, G. Now, the question is, so you have like your main course, right? Maybe it's a big steak, and then you have F and G on the side, okay, whatever that is. All right. The question for you is, does it really matter if you list it as F and G or G and F? The answer is no. It's still the same 2 damn side dishes. We're only interested in, whether or not you end up with the same 2 side dishes. The order by which you list them does not matter. Let's say F is broccoli rabe and G is mashed potatoes. Well, if you end up with broccoli rabe and mashed potatoes as your 2 side dishes, well, those are your 2 side dishes. Does it matter if you listed it as mashed potatoes first and broccoli rabe second? No, you still have the same 2 damn side dishes, right? So this is a pure example of choosing 2 from a group of 8. Choosing a smaller amount from a larger population in such a way that the analysis that we're performing is such that the order does not matter. All right, so hopefully that makes sense. Let's see what the answer is. A combination because order does matter. No, that's out of here, because when you have a combination, order always matters. I mean, that's the whole point of a combination. Combination because the order doesn't matter. Yeah, so a combination because the order doesn't matter. That's what I meant. Hopefully I did not misspeak before. But anyway, this is the answer. It's going to be a combination because the order doesn't matter. Moving. Let's see. The president of a college conducts a survey of all college employees to determine how they feel about building a new gym. The president can only, um, I think that's a survey, a fraction of the employees, which constitutes the most appropriate random sample. All right, so basically, when you're dealing with random samples, that means, you know, okay, so in statistics, uh, in the case of this president, this president literally will never be able to survey all of the college employees. No one's got time for that. There might be hundreds of these college employees. So what the president has to do is the president has to randomly pick from the crowd of total college employees and sort of hope, well, maybe more than hope. Statistics is the mathematical science of more than hope. But the college president wants to pick enough of a group of college employees such that whatever that sample is will hopefully be representative of the total college employees, right? And the best way to avoid bias is to pick randomly from college employees. And there's multiple ways of picking random samples. So let's investigate these answer choices, but first let's once again get clear about what is being asked. Which would constitute the most appropriate random sample for the survey? So let's investigate. Who are listed on the college employment roster? People who work out in the current gym every day, and students who use the gym regularly. Random selection of employees and students who are members of the physical education department. Well, first of all, the things that mention students can get the hell out of here, okay? Because we're not interested in students. Yeah, I don't know why we're all of a sudden bringing students into the equation. This has to do with college employees. That's the only thing that we're analyzing. It is a survey of college employees to find out how they feel about something. This has nothing to do with students. So already, answer choice 3 and 4 are gone. Looking at answer choice 1 and 2 again, who are listed in the college employment roster, who work out in the current gym every day. All right, so the answer is this one. And before I get into why, we're going to take a look at why this one is not the answer. The reason this is not the answer is because that's kind of a weird thing to do, like to pick the college employees who work out in the current gym every day. These people are going to be super biased, all right? Because we're doing a hopefully random sample of how college employees feel about building a new gym. Well, what if these people who work out in the gym, current gym every day, have a strong opinion? Maybe they love the current gym, right? So they're going to be a biased sample. That is a classic case of a biased sample. So if the president really wants to know how college employees in general feel about building a new gym, we don't want there to be a biased sample. So therefore, you could say by process of elimination, this is the answer. But also you could look at it and be like, well, clearly that's a great way of picking a random sample. Yeah, you just look at the college employment roster, which includes hundreds of employees, and treat it like a lottery. You just pick out, random employees from that whole roster. Moving on. Question 10, probability statistics. Consider the following 5-number summary from an array of 100 test scores. What can be inferred from the summary? Yeah, so minimum is 38, 61. Yeah, okay. So let's just put it this way. 38 is the lowest test score according to this piece of information. 98, it looks like, it's a little blurry, but 98 is the largest test score according to this information. The median test score was 75. So we're going to put that in the middle. And the first quartile was 61, and the second quartile was 87. So basically, this quartile means that about a fourth scored 61 or less. This quartile means that about 3/4 of the students, or exactly 3/4, I'd have to double check that, scored 87 or less. Okay, that's what these quartiles mean. So we're going to put Q1 right here. We're going to put Q2 here. So let's take a look at the answers. 1/4 of the scores are between 38 and 75. No, no, that cannot be inferred from this information that 1/4 of the scores are between these two. 1/4 of the scores are between 75 and 98. For the similar reason, that cannot be inferred either. Half the scores are between 61 and 87. Let's see. That can be inferred because we have 1/4 here, another quarter here, another quarter here, and another quarter here. And, you know, this is a quarter, and therefore this would be half, because a quarter plus another quarter gives you a half, right? So between 61 and 87, that is indeed half of the scores for sure. Half of the scores are between 38 and 98. Let's just take a look at that. Well, no, friggin' all of the scores are between 38 and 98, so that one's gone. So the answer is this one. There's more to be said about quartiles and stuff like that. But I'd rather move along and sort of rely on this simplistic version of just like a visual and even somewhat intuitive approach to the problem to save time. Probability statistics. The following table lists all the possible outcomes for a random spin of the wheel along the probability of each outcome. What is the expected value for the outcome of a spin? All right. So basically, let's say there's a gambling situation, and there's a wheel, and this represents literally the points that you can get on the wheel. Like, for example, maybe the wheel looks something like, I don't know, friggin' this. Right? Where the probability of getting 1 point, you know, it's like a Wheel of Fortune wheel. You know, if the ticker lands on this point, you get 1 point, right? The probability of getting 2 points is right here. The probability of getting 3 points is right here, and the probability of getting 4 points is right there. And that should make sense because, you know, there's a 0.1 chance of getting 4 points. Well, that means that this is the smallest pizza slice. The chances of getting 4 points on a single spin are pretty low. Right? Now, they're asking, what is the expected value for the outcome of a spin? Now, expected value basically means if you were to spin this like literally an infinite amount of times, what is your average score going to be at the end of the day? You know, is it going to be 1 point per spin? Is it going to be 2 points per spin? You know, what's your average score per spin? You know, what would that be in the long run? So expected value has to do with in the long run, you will get how many points per spin. The good news is that you can use a very relatively simple formula to figure that out. And that will always be the score times the probability of getting that score plus the next score times the probability of getting that score plus the next score times the probability of getting that score, plus the next score times the probability of getting that score. You're going to add all that up, and that's going to give you your answer. I'm not going to do it right now, but you get the idea. Okay. Attendees, let's see. Attenders at an event where either a red shirt or a blue shirt, a student records the number of red shirts and blue shirts broken down by age of the attender. The result is blah. What is the probability rounded to the nearest hundredth that a randomly selected attendee will be 40 years old or older wearing a red shirt? Right. Let's quickly remind ourselves that probability is desired outcome all over the possible outcomes. Now, you may recall that I said before, it's often easy to sort of figure out, well, what are the possible outcomes? And let's just think about that first, right? So if we want to do the probability, what are the possible outcomes? Well, that would be, you know, if we want to know, you know, what's the probability that a randomly selected attendee will be 40 years old or older and wearing a red shirt? Well, as far as the possible outcomes go, that would be the total amount of people in general, right? However many people are there in general. Unfortunately, we're going to have to add this. Let's see, we're looking at 24 plus, I'm going to pause the video and add this right now. Okay, so I added up the total amount of people that we're even looking at, and it turns out that it's 318. All right. Now, let's get clear on the desired outcome. In other words, the specific outcome that we are analyzing right now. And that is, we want to look at a randomly selected group of attenders that will be 40 years old or older and wearing a red shirt. Well, it's a red shirt, so we know it's going to be this row, and then it's 40 years old or older. So that's going to be this cell and also this cell. That's the tricky thing about this problem. You want to make sure you include this cell too, because the people who are 50 to 59 years old, well, that's 40 years old or older, right? So this is going to be 81 plus 51, which is 132, right? And then you would just sort of divide that, come up with the decimal version of that, and that's going to give you the answer. Okay. Which best describes a preference schedule? Okay, we haven't spent a lot of time on this voting stuff, but basically a preference schedule is when voters not only choose the candidate that they like the best, but they also rank the candidates in the order that they like. So let's take a look. A summary of preference ballots cast by voters, a summary of the number of first place votes, an ordering of candidates submitted by the most voters, an ordering of preference ballots based on the time the ballot was. Yeah, so this is just this one. It's kind of a weird problem. A summary of preference ballots cast by voters. So preference schedule is the summary of preference ballots cast by the voters. Now, why did I not choose these other ones? Let's look at this one. A summary of the number of first place votes received by each candidate. Well, first of all, it's a preference ballot / schedule, so that has to do with more than just first place votes. That has to do with ranking the candidates. Answer choice number 3, an ordering of candidates submitted by the most voters. Well, I don't know this whole thing about the most voters. I mean, no. Preference schedule, preference ballots has to do with all the voters, right? We're taking into account the perspective of all the voters, not most voters. So this one's gone. And ordering of preference ballots based on the time. All right, based on the time, what the hell does preference schedule or preference ballots have to do with based on the time? So that is a bunch of BS right there. So that's gone. So simply by process of elimination, you could also choose answer choice number 1. All right, moving on. All numbers are either odd or even. If all composite numbers are even, then which must be true? Huh. Let's see. Yeah. Okay, well, all numbers are odd or even. Here is the group of all odd numbers in this circle. Here is the group of all even numbers in this circle. Notice how these circles do not overlap because odd is mutually exclusive with even. You can't have a number that is both odd and even at the same time. Okay? All composite numbers are even. Well, guess what? If all composite numbers are even, I am going to draw a little blob in here that represents composite numbers because all of them are even. So we can do that. We can put all the composite numbers in here. Now, there's other numbers that might be even, but definitely all of the composite numbers fit inside this bubble, right? I like visualizing these statements in this way because it really helps get clear on what the hell is going on. If a number is even, then it must be composite. Must that be true? Hell no, because here's a number that's even that's not composite. You know, there's a lot of numbers out here that are even, that are not necessarily inside this blue bubble, right? So that answer is gone. By the way, there's 3 correct answers here. If a number is composite, then it must be even. Absolutely. Bam. Why? Because here's all the key composite numbers over here. Well, clearly, this is freaking even, right? If a number is even, it might be composite. Yes. Yeah. Because if a number is even, that means it's in this bubble somewhere. Might it be composite? Well, yeah. If it ends up here, sure. Okay. I hope you guys understand my blathering. Okay, if a number is odd, it cannot be composite. Well, if a number is odd, it's over here. Is it the case that it cannot ever be composite, therefore? Absolutely. This bubble is not even close to this bubble, right? So it's, well, it doesn't overlap with this bubble. Let's just put it that way. So that's the answer. I don't even need to read this one because there are 3 that apply. We're done. In baseball, the earned blah, blah, blah is a measure of a pitcher's effectiveness. The formula for blah, blah, blah is this. So they give you the formula, which will make things easier. If after pitching 180 innings, a pitcher's ERA is exactly 3, how many earned runs did that pitcher allow? Well, earned runs, which is, by the way, what we're looking for, is right here. Innings pitched, which they give us, it's 180 is right here. They also give us the ERA, which is 3. I think they would have been a lot nicer to complete this equation by writing ERA right here, okay? So this is the formula that we use to find the ERA. ERA equals 9 times earned runs allowed all over innings pitched divided by innings pitched. Now we have a nice complete formula that would allow us to solve this problem. So let's set it up. The ERA, instead of ERA, I'm going to write what they give us as the ERA. The ERA is exactly 3, so we're just going to write 3. We're not going to go 3.00. And this could be 9 times something, so let's just write that. 9 times some fraction. What is that fraction? Well, it's earned runs allowed. Well, by the way, how many earned runs did that pitcher allow? Well, we don't know, right? That's the unknown, so we're going to put a big fat X there, so this is already algebra. If after pitching 180 innings, well, innings pitched goes on the bottom, that's 180 innings, right? So this is 9 times x over 180 equals 3. Okay, so this is algebra stuff. When you want to solve for a variable, you want to get this variable by itself. It behooves you to simplify both sides of the equation first. This side of the equation is already as simplified as it could be. This side is not as simplified as it could be. We could simplify this 9 and this 180. So 9 could cancel out and become a 1. 180 could cancel out and become a 20. So what we're really dealing with is x over 20 equals 3. So this 1, we could sort of dismiss it because 1 times whatever results in this thing just being itself. So we don't need to really write 1 times something. So on the next line, we're not going to write 1 times something. We're just going to write this so it looks a little better. What we're really dealing with is x over 20 equals 3. Now, if we want to solve for x, you got to get x by itself. It's not by itself because we have a 20 underneath. X is currently being divided by 20, so in order to get rid of that 20, you have to do the opposite operation to both sides, which is to multiply by 20. And the reason you want to do the opposite operation is because that cancels with this 20 that's down below, which is the entire point, because that now leaves x by itself. So let's take this up here. We end up with x equals, well, what does it equal? It's going to equal 3 times 20, which of course is 60. That is the answer. Bam. Which are included in Polya's steps for problem solving. So Polya's steps for problem solving is not the most well-known kind of thing, but for this test, it looks like you're going to have to memorize it. And basically, Polya's steps for problem solving are the following. First, you got to prepare, understand the problem. The second step is you have to think, devise a plan. This third step is you have to carry out the plan. And the fourth step is to keep trying until something works and verify, look back, right? So I just mentioned a whole bunch of things. The first step, once again, was understand the problem, which is represented right here. Devising a plan, well, that's represented right here. Carry out the plan, let's see. Yeah, so actually we are noting which ones apply. So understand the problem, devise a plan, and then the last step is to look back, verify, check your answer. So that's the last step. I'm going to write that right here, whatever. Understand the problem. That's step number 1. A lot of the stuff we already know. Thinking, devise a plan. We'll call it devise. plan. And then the third step is carry out plan. I feel like a lot of this is obvious, but I'm sure it comes into play sometimes in maybe more complex situations. The key is keep trying until something works, and then verify. Look back, check your answer, verify. So these are the 4 steps. We already marked 3 of them. There's no mention of reducing answer to lowest term, and there is no mention of eliminating the cause from the problem. So those are not included in our answer selection. Moving on. Let's see. A 40-minute CD contains 10 tracks. The longest track is twice as long as the shortest track. Without the shortest track, the CD would be 37 minutes long. How long is the longest track? Which piece of information is unnecessary for solving the problem? Notice how they're not asking us to solve the problem. They just want to know which piece of information is unnecessary to solve the problem. So let's get a picture of what the hell is going on with this problem. Maybe it's because I kind of dig Singapore math. I like the whole unit bar approach to certain problems, so I'm going to bust out a unit bar right now. 40-minute CD contains 10 tracks. All right, so we got the 40-minute CD right here. And let's just keep in mind, it features 10 tracks. All right. But one thing we know is that it's 40 minutes long, right? 40 minutes. And then they're like, the longest track is twice as long as the shortest track. All right, I'm going to make a mental note of that. Longest track, twice as long as the shortest track. Without the shortest track, the CD would be 37 minutes long. So we're going to model a CD only without the shortest track. And this one happens to be 37 minutes long, right? Now, immediately, we can see that there is this 3-minute disparity. And you know what that means? That's how long the shortest track must have been, right? Shortest track must have been 3 minutes long, because according to this information, if you have the longest track and then you take out the shortest track, you go from 40 minutes to 37 minutes. So anyway, how long is the longest track on this CD? Well, we know the shortest track is 3 minutes long. We also know, according to this information, that the longest track is 2 times the shortest track. So we could actually do this. We could actually be like, all right, well, if the longest track is twice the length of the shortest track, we already know the length of the shortest track is 3. Therefore, the longest track is 2 times 3, which is 6. That is the longest track, right? Longest. So, great. Which piece of information was unnecessary? The fact that it was a 40-minute CD? No, we needed to know that to solve this problem, because we needed to know 40-minute, 37-minute disparity, 3-minute disparity. The fact that we have 10 tracks, did we need to know that? Hell no. We did not need to know that there are 10 total tracks. This problem could have worked if we had the shortest track here, the longest track here, and maybe the medium track here. So in other words, for all we know, there are friggin' 3 CDs on this track. We did not need to know that there are 10 tracks. That was extra information. So that piece of information was completely unnecessary, and therefore that is the answer to this problem, because we want to know which information was unnecessary. Let's investigate 3 and 4, though. The longest track is twice as long as the shortest track. No, we needed to know that. We took that into account over here. Without the shortest track, the CD would be 37 minutes long. We definitely needed to know that because we needed to recognize the 3-minute disparity. Moving on. If A is greater than B and B is greater than C and B is less than D, which of the following must be true? All right, I could get to that, but immediately I am annoyed by the fact that we now all of a sudden have B is less than D. I would rather list this stuff in the same sort of way, where the stuff that is, in fact, you know what we're going to do? We're going to list it from least to greatest, because that's a little bit easier on our brain. So instead of writing A is greater than B, you know what I'm going to write? I'm going to be a rebel, and I'm going to write B is less than A, right? Because we're kind of used to seeing like the smaller thing over here getting greater, greater, greater as it goes in that direction. All right, so that's what we're going to do. I'm going to write it that way. Let me X this out. And just know that that's what I'm doing for all of this stuff. So it's like, instead of A is greater than B, I'm going to write B is less than A. Instead of, B is greater than C, I'm going to write that C is less than B. And then B is less than D, I'm going to write that right now. B is less than D. Yay. All right. Already looking at this, analyzing this without even getting into the answers, B is less than A. What can we immediately assume? If B is less than A and C is less than B, well, guess what? C has to be less than friggin' A, right? Because here's C less than B, and B is less than A. So guess what? C is totally less than A. So we know that for a fact. In fact, I would rather just leave this looking like this because this little thing tells us a lot of information in one shot. We also know that B is less than D. All right, so it's like B is less than A, great. B is less than D. Now, we don't know if A is greater than D or not, but we do know that A and D are both numbers that happen to be larger than B. But you know what else we know? If D is greater than B, then guess what? D is greater than C. You know why? Because friggin' B is greater than C, right? How do we know? From the earlier pieces of information, right? So we could also set up this structure right here, right? Let's see if that helps us. Can we know for sure that A is less than C? No. In fact, we know that A is greater than C. Can we know for sure that C is less than D? C is less than D. Yes, we can know that for sure. Done. Moving on. Okay, so let's see. If today is Tuesday, what day will be in 69 days? Okay, this one could be a little tricky. Let me get a sense of blocks of days because we want to avoid counting all this, right? So we want to find out how many weeks we could say fit underneath or within 69, something along those lines. So let's analyze blocks of days. So we've got Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. So that is a block of, and Monday. Whoops. That is a block of 7 days, right? That, we're going to be sort of repeating over and over. But let's take a look here. We want to know, if today is Tuesday, what day will it be in 69 days? That's interesting wording. So it's like in 1 day, it's going to be Wednesday. In 2 days, it's going to be Thursday. In 3 days, it's going to be Friday. So, I'm thinking in 1 day, it's going to be Wednesday. In 2 days, it's going to be Thursday. In 3 days, it's going to be Friday. In 4 days, it's going to be Saturday. In 5 days, it's going to be Sunday. In 6 days, it's going to be Monday. And check this out. In 7 days, it's going to be Tuesday, right? This structure right here should provide you with the key to finding the answer, because what we could do is we could find out how many of these blocks of 7 fit inside 69 and then consider the remainder. So let's find out how many blocks of these 7 fit inside 69. 7 times 9 gives me 63, which gives me that remainder of 6. So in other words, this to my student, 9 of these blocks would fit in 69 days, but then there's this remainder of 6, which means we need to count 1, 2, 3, 4, 5, 6 over. So you can think of it as, 7 of these blocks, or no, what is it, 9 of these blocks of 7. What's that? 1, 2, 3, 4, 5, 6, 7, 8, 9, and we're dealing with 7, right? So it's like, I always do the middle one first. If you're drawing like odd stuff, do the middle one first, then we're going to have 3 on each side, flanked by 3 on each side, right? So you could think of it as, 9 times 7 block. It's nine rows of these 7 blocks of 7 days. This would be Tuesday, Wednesday, Thursday, or Wednesday, Thursday, blah blah blah, and then it's the additional 6 days down below that we're considering, and this is where we would land, right? And that corresponds with Monday, so that would be Monday. Hopefully that makes sense. That one's a little weird. Okay, a cost to rent a truck is $29.95 each day plus 79 cents per mile. Which mathematical model describes that scenario? So we know for a fact that we're going to be spending $29.95 each day no matter what, right? So these are formulas that represent the cost. The cost equals blah, 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 blah. The cost of renting this truck will equal blah, 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 blah. Well, it's going to be $29.95 no matter what. And then on top of that cost, it's going to be 79 cents per mile. Answer choice 1 is gone because we're going to be like, wah, because it's 29.95 times the amount of miles you drive. No. We're spending only $29.95 as a baseline, and then on top of that, we have the variation, right? So this is gone. Let's see, $29.95 plus 79 cents per mile. Hell yeah, that is exactly what we will be spending. It will be $29.95 no matter what. And then depending on how many miles, which is X, you're going to be spending 79 cents per mile. We do not even need to look at the rest of the problems. Moving on. Let's see. P and Q represent the following simple statements. P, he is elected mayor, taxes will increase, which corresponds to taxes will not increase if he's elected mayor. This has to do with your ability to read this kind of like logic truth statement-y type language, which is a concept you don't really get introduced to unless I think you're in college. I think it's kind of rare that you'd get introduced to this in high school. But it's not that bad. Just know that anytime you see P, that means the following statement. He is elected mayor. Anytime you see Q, that means the statement, taxes will increase. Anytime you see a squiggly line like that, it means the opposite of that statement. Anytime you see an arrow, it means if this, then that. If this, then that. And that's all we need to know at this point. So, taxes will not increase if he is elected mayor. Okay, they're being tricky with us where it's like they're putting the if statement over here and the then statement over here. So I think it would benefit us to rewrite it as if he is elected mayor, then, what is it? Taxes will not increase. Well, already, we know this then is going to be like an arrow, right? So, if this, then blah. So, if he is elected mayor, well, he is elected mayor is P. So, we're going to put a P there. And let's see, taxes will not increase. Well, this says taxes will increase. So the opposite of taxes will increase is taxes will not increase. So squiggly line Q. Now they're doing a double squiggly line, which I've actually never seen before. I'm used to seeing a single squiggly line, but I'm going to assume that it means the same thing. I don't know. Hopefully I'm right about that. So we're looking at P, arrow, squiggly line, Q. Bam. That's the answer. Moving on. A person drives north 2 hours at 50 miles an hour, rests for an hour, then drives west at 30 hours, 50 miles an hour. How far did the person drive? Right? Which piece of information is unnecessary? So this is another problem where they don't even necessarily need you to solve the problem. They just want to know which piece of information did you not need in order to solve the problem, right? Well, let's at least sort of make some headway with solving the problem. Maybe we're not going to go all the way, but we'll at least begin so as to get a sense of what is necessary to solve the problem. Let's say the person starts here, the person drives north for 2 hours at 50 miles an hour. By the way, rate times time equals distance, right? And, if the person's going friggin' 50 miles an hour, times 2 hours. I mean, we definitely know that this person went a friggin' 100 miles in that direction, right? Then he drives west for 3 hours at 60 miles an hour. Well, that would be over here. 60 times 3 hours, right, equals 180 miles, right? So we are kind of making some headway. And then, what does it say? Oh, rest for 1 hour, right? So he rested for 1 hour, she rested for 1 hour here, then she went west. How far did the person drive? Now, that's, to me, a little vague. If we were to actually answer the question, I feel like we would kind of need to know. I guess that it's referring to, actually driving on the road, so never mind. Yeah, so we actually did kind of solve the problem. It's going to be 100 plus 180. That's going to be 280. So we actually have the answer. Which piece of information was unnecessary? Did we really need to know that the driver rested for 1 hour right here? Absolutely not, because that has nothing to do with how far the person drove, right? So resting for 1 hour was unnecessary information. Therefore, this is the answer. What is the next number in the pattern? My student is very, very good at solving patterns, but for those of y'all out there who might not be, let's see, between 99 and 98. I mean, a good first thing to try is to just find the difference between these two. So it's like 99 minus 88 is 11, 88 minus 75 is, what's that, 13, 75 minus 60 is 15, 60 minus this is 17, so guess what? It's going to be 43 minus 19, whatever the hell that is. It's in there. Graph theory. What is the degree of vertex A? In other words, if you were to zoom in to this vertex A, really close, how many little roads would be popping out of it? That's what they're saying. Well, there's this road, 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 and there's this road. 1, 2, 3, 4, 5, 6, 7. Guess what? We can end our investigation right now. The degree of A is 7. Moving on. For the graph below, which is an Euler circuit? Okay, first of all, the way to pronounce it is Euler, not Euler. It doesn't rhyme with Ferris Bueller. It is Euler, so that's the first thing. Circuit is when you start somewhere and you go through all this stuff, and then you end up back where you came from, okay? So just based on the fact that we're dealing with a circuit, I'm not even going to worry about the fact that it's an Euler circuit. I'm only concerned with the fact that it's a circuit right now. Which answers can I eliminate just based off of that information? Well, if it's a circuit, that means we started somewhere, and then we blah, 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 went through this thing, and then we ended up at the same position at the end. Well, which of these answer choices feature scenarios where that does not happen? Well, this is a circuit because we start at E and then we end at E. So this is a circuit. This is a circuit because we start at E and we end at E. So that's a circuit. This is not a circuit because we start at E and we end at O. So that's not a circuit. So right out the gate, this is gone. And this is a circuit because we start at E and we end at E. So we're down to these three answer choices. So that brings into analysis the concept of Eulerness, right? So basically, Euler circuit and let's say an Euler path and or circuit, it's basically when you hit every edge, okay? And an edge is either the line or the curvy thing. So if you go through the motions, right, and you go to these vertices and you end up hitting every edge exactly once, that's the other thing. It's got to be hitting every edge exactly once. That is an Euler scenario. Now, if it's an Euler path, it just means you hit every edge without necessarily going back to where you started. If it's an Euler circuit, it means you hit every edge exactly once, and you also happen to go back to where you started. Now, my thought is before I get into the weeds of analyzing all this crap, I'm looking at this part. I'm thinking to myself, well, there has to be a moment where you're on A, and in order to hit this circular edge, you got to be on A, and then you end up on A again. There's going to be a moment in this whole path where you hit A, and then you have to go around this in order to hit that edge, and then you end up at A again. So whatever the answer is, it has to be something that has a double A listed. Because this says you go from E to A, and then from A to D, and then from D to E, yay, blah, blah, blah. But what about this circle thing, right? The only answer choice that features the double A that we need is this answer choice, where it goes A and then A again. So this moment right here, this moment is where you went around the circle. Since it's an Euler circuit, we have to go around the circle at least once. That necessitates doing A and then A again. The only answer choice that features the double A is this one. Now, it took a long time to explain that, but once you understand that thinking, you will immediately be able to just eliminate the crap out of these other answers in like 2 seconds and know with full conviction that the answer is number 4. That's why I harp on this. Okay, so a graph cannot have an Euler path if which condition about the graph exists? I was going to go over this picture, but I don't think that's a good idea. I think what we need to know is the following. When it comes to Euler paths, not circuits per se, but paths, in order for it to have an Euler path, I'll just write Euler path. It must have exactly two odd vertices. All right, that's it. If this criteria is not fulfilled, if the graph does not have exactly 2 odd vertices, you don't have an Euler path in that graph. So, a graph cannot have an Euler path if which condition about the graph exists? Well, let's investigate. It has only one odd or one even vertex. Well, I suppose it could exist. An Euler path could exist in that scenario. So we're going to say that that's not one of the answers because the Euler path could exist. We're looking for where the Euler path cannot exist. So we're eliminating this because the Euler path could exist under that circumstance. It has only one odd vertex. Well, in order for something to be an Euler path or have an Euler path, the graph needs to have exactly 2 odd vertices. So if it has only one, then there's no way in hell that an Euler path exists. So this works as an answer because this criteria describes a scenario where you cannot have an Euler path. So get the next one. It has more than 2 even vertices. Well, I would say in that case, you could definitely potentially have an Euler path. So this one is gone because you might be able to have an Euler path under those criteria, that criteria. We're looking for criteria that is such that you cannot have an Euler path. So look at the next one. It has more than 2 odd vertices. Well, in order to have an Euler path, you got to have exactly 2 odd vertices. So if you have more than 2 odd vertices, then it makes it so that you cannot have an Euler path. So therefore, this would be an answer as well. I find that these are confusing problems because it's like, which of the answer choices is such that you cannot have an Euler path? So it's literally the moment you find out that something cannot have something, that's the answer. So it's kind of like reverse. It's like the opposite of what we're used to doing when it comes to like marking down answer choices. You're so used to looking for like the answer, not the answer of when something can't happen, right? So you do have to kind of like be very, very meticulous, very careful, maybe even underline words like I did, you know, which graph cannot have an Euler path? Like really highlight the fact that we're looking for the criteria that is such that it would be impossible to have an Euler path, right? And to take it from there. Let's see. A table below shows the distance in miles between pairs of 4 schools. A, B, B, B. Use the nearest neighbor method. Starting at A, how many miles are required to travel to each school and then return to point A? All right. Well, these tables are pretty easy once you get used to them, where you're starting at A. Let's map the path out, right? So you start at A. Here's A. And then where we're going to go? Well, we're going to use the nearest neighbor method. So we're going to go to the place that is the closest. So the place, looking at this column, let's use columns for now. We start at A. The closest place is C. It's 5 miles away. So we go to C. The next closest, once we're on C, we're going to stick with columns. What's the next closest place? We could say it's A, but we've already been to A. We want to go to all the other letters. So the next closest place that we haven't been to is B. So we're going to go to B, right? Okay, now we are on B. Where is the next closest place that we haven't been to? Well, we've already been to A. We've already been to C, so that actually leaves only one place. It is D. So we go to D. But guess what? Now we have to go back to A, right? Because according to the problem, what does it say? We return to point A. So we got to go back to A. Here's us going back to A. Let's draw little arrows, and we're going to write the distance traveled, right? Because we want to know what is the distance traveled. So from A to C, it was, 5 miles. From C to B, it was 9 miles. From, B to, D, that was 4 miles, right? And then finally from D to A, as you can look, that is 11 miles, right? So nearest neighbor method is when you go to the nearest neighbor from where you are. Now, you do have to, according to the constraint to the problem, you do have to hit a place you haven't been before, right? And you also have to go back to A at the end, regardless of how far away you are. You know, D might be really far away from A, but guess what? We still have to return to point A once we've hit all these other letters, right? So anyway, calculating all this, 5 plus 9 is 14, plus 4 is 18, plus 11 would be 29. So the answer is 29. Bam. Which is necessary for a graph to have an Euler circuit. So we had already talked about how in order for a graph to have an Euler circuit, it needs to be connected, and it has to have every vertex having an even degree. All right, so there can't be any odd degree vertices in the graph in order for it to have an Euler circuit. So I would say this answer applies. It's got to be connected and every vertex is of even degree. I would say this answer applies. I would say no odd degree vertices. That answer would apply. Connected with an even number of edges and an even number of vertices. This one does not apply. We do not need to concern ourselves with the number of edges when we're considering an Euler circuit. So the answer is answer choice 1, 3, and 4. For the graph below, what is the weight of the Hamilton circuit starting at vertex A found by the nearest neighbor method? So Hamilton circuit is when you're not really focusing so much on hitting every edge exactly once. That would be more of an Euler scenario. The Hamilton scenario is when you're more concerned with hitting every vertex exactly once. So it's kind of like being a paperboy and making sure you go to every house without repeating the houses, right? And it is a circuit, so that means we got to start end where we started. So we start with vertex A, and if we're going to use the nearest neighbor method, it would go from A to, B, it looks like, because from A, it is only 5 units to B. And then from B, we have 3 choices. We could either go to A, we could go to C, or we could go to D. It looks like C is the next option because from B to C is 2. From C, we have 3 options. We could either go to, well, actually, we only have 1 option because we have to hit D, don't we? So from C to D, it's going to be 8 units, which we'll take into account. And then finally, since it's the Hamilton method, we got to hit every point exactly once. We actually just did that, and now we have to go back to where we started, which is A, right? Now they want to know what is the, what is the weight of the Hamilton method? Well, the weight is, in a sense, how much distance you traveled in that path using the nearest neighbor method. This is almost like the table problem that we did before, only visual. From B to C, it's 2. From C to D is 8. From D to A is 9. And then you just have to add all that up. You'd get, 7, 15, 24. So it's going to be 24. Okay, so this one is asking which graph has the following pairs of adjacent vertices and no other pairs. Okay, so first of all, adjacent vertices. That means that you have two vertices that are connected by a single edge. In other words, adjacent usually means kind of like, I don't know, next to or connected to, for example, if I have a house and my shed, if I have a lopsided house, front door right here, and my shed is adjacent to the house, that means it's like connected to the house. Here's the shed right there, adjacent to the house, right? So I think carpenters probably will use the word adjacent quite a bit, I would imagine. Anyway, so if we're looking for adjacent vertices, we want to know, for example, look at D and C. Where are they adjacent? Well, here's an example of where D and C are adjacent because they're right next to each other and they're connected by a single road. We could say connected by a single road. Now that road could be curvy, it could be straight, but we know that D and C are a pair of adjacent vertices because they're connected by a single road, right? Now, the big pair that stands out to me is AA. In order for A to be adjacent with itself, you know what that means? That means we got to have a friggin' vertex of A, and if it's adjacent with itself, guess what that means? There's a road that swoops around and then hits A again, right? That's the only way that A is going to be adjacent to itself. So my thought is, let's eliminate all the graphs that do not feature this curvy, loopy thing, right? And of course, that would include eliminating this one, this one. Let's see, this is not what we're dealing with. These are the other answers. So it's kind of annoying. Let everyone who's watching just disregard this, and we're going to look at these two answers, because actually these are the two answers that are left. All right. Okay, of course that happens. So here we are. We've got this. And then the question is like, okay, well, what is the correct answer? Well, let's investigate the other situations right here. So we've got B and C. Is B adjacent with C here? No. So already right out the gate, this one's gone because it is not the case in this graph that B is adjacent to C, where B is supposed to be adjacent to C, according to this information. So I just eliminated that, and of course, by process of elimination, we have our answer right there. Honestly, at that point, to save time, you don't even really need to analyze this thing, right? If you've eliminated everything else, you're done. Okay, so which is an example of an odd vertex? Well, first of all, the degree of a vertex is having to do with how many edges touch the vertex, right? I had mentioned earlier we had a vertex, let's call it A. If you've got, 4 edges emitting from A and maybe connecting with other vertices, all over the place, it's just a matter of sort of zooming in on A until you could very clearly see how many edges are emitting out of A. In this case, there's 4. 1, 2, 3, and 4. So that would make A an even vertex, right? So if a vertex has an even amount of edges emitting from it, that means that it is an even vertex. So an odd vertex would be, a vertex that has an odd amount of edges emitting from it. In fact, let's make this odd right there. Bam. Okay, so let's look at the answer choices. Which is an example of an odd vertex? An isolated vertex of a disconnected graph? No. I guess that vertex would have 0, right? Because it doesn't have any edges coming out of it, right? Basically what that means is you got a graph like this, blah, 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 and then you got some isolated bastard over there. And basically what they're saying in answer choice number 1, is that an odd vertex? And the answer is no, because there's no edges coming out of that thing. Okay. Answer choice number 2, a vertex has 5 edges attached to it. Yes, ding, ding, ding. That is most definitely one of the answers, at least. A vertex with an edge starting and ending at this vertex. No, because here's a vertex. Here's an edge starting and ending at that vertex. Well, guess what? That has a friggin' degree of 2. Why? Because when I zoom in, zoom, 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 and I analyze, how many roads are coming out of this thing? There's 1, and then there's another one over here. So that would be two edges emitting out of it. Now, maybe my wording's confusing because in the big picture it looks like maybe it's like one road, right? But again, we want to emphasize what it looks like when you zoom in very closely. How many things are emitting from the vertex? In this case, there's two. So it has a degree of 2, which, by the way, is, of course, an even number. So it's even, not odd. A vertex which, when removed from a connected graph, would leave a bridge. That is not part of the criteria of an odd vertex, right? I mean, if we removed A, it's not like we would create a bridge, okay? So anyway, therefore the answer is, I marked it over here, but we're going to do it again. This is the answer. Which correctly describes the following graph? Okay, well, this is one single graph. I know it looks like two graphs, right? But believe it or not, this is one single graph that happens to be disconnected. All right? So which correctly describes the following graph? The graph is connected? Hell no, it's disconnected. The graph has even degree vertices. I don't know, let's check. B is a vertex, it's even, it's got A, and it's got C coming out of it. So yeah, that works. And I'm gonna use blue for the correct answers. The graph has odd degree vertices. Yes. How do I know? Well, looking at A is an odd vertex, right? C is an odd vertex. Okay, the graph has a loop. Yeah, right there, at least. Loop it up. The graph has one component. No, it has two components. Here's one component and here's another component. So of course that requires you understanding what a component is. A component is a piece of like a disjointed graph. So it's got two components. Moving on. Oh, looks like that's it. Okay, so that's the video. Hope you guys liked it, and I'll see you later.